Okay, we're going to continue on here. Chapter 16 got into something different for once, maybe a little. Some thermodynamics. And so remember that when we talk about thermodynamics, oftentimes what we're sort of looking at is whether or not a reaction is spontaneous or not. And remember, as we talked about last time, when we kind of talked about whether or not something is spontaneous, again, it does not have to do with how fast or slow it takes place. It's basically just that under those specific conditions, the way the reaction is written, that reaction should take place without any sort of, again, outside sort of interference or anything like that. And that is, again, what spontaneous means. Again, you can have spontaneous reactions that are kind of slow and you can have some that are fast. But in this aspect, what it means when we talk about spontaneity is that reaction should take place the way it's written under those conditions. And what that also essentially means in most cases is it would be heading from reactants to products. How it's written is what you would sort of expect to happen. Obviously, if a reaction is non-spontaneous, the opposite is true. We would not expect under those conditions without any sort of outside help, if you will, for the reaction to take place. So we talked about a couple of sort of thermodynamic values. One that you've seen before, which obviously is delta H, which is our change in enthalpy, kind of the heat of the reaction. And remember, again, if the delta H is negative, that's going to be an exothermic process. If the delta H is positive, it's going to be an endothermic process, which means heat and energy would be absorbed as opposed to release energy in an exothermic reaction. We then sort of talked about the idea that we can't necessarily use enthalpy itself to determine whether or not a reaction is going to be spontaneous, as exothermic reactions do favor a reaction being spontaneous, but there are definitely reactions that are spontaneous that are endothermic as well. Um, and again, energy is sort of the first law of thermodynamics, the conservation of energy. We cannot create it nor destroy it. One of the things that helps with reactions sort of being spontaneous, and that's why necessarily exothermic reactions a lot of times helps favor spontaneity, is the idea of sort of spreading out energy. And as energy sort of spreads out, so does everything else. Species sort of spread out and stuff like that. And that sort of helps in things being spontaneous. Having just the spread out of more energy moving around helps everybody kind of start moving around and start reacting and stuff like that. So it's very favorable. So we then talked about a new sort of value, which is delta S, and that is the entropy. And again, not to be confused with the enthalpy. And delta S is all about really disorder and the craziness that happens in the world. So as the amount of disorder increases, uh, delta S in that case actually becomes more positive. So that's also maybe a little bit different than you might think. So when there's a lot more disorder, a lot more craziness, not a lot of order happening, we do end up seeing the entropy value become more positive, and vice versa. As the amount of disorder decreases, which by default would mean you're having a lot more order happening in that situation, we do see the change in the entropy becoming more negative. And a couple of things about the units that we perhaps touched upon, and we'll touch upon again. Enthalpy is in kilojoules, is typically the units that are associated with it. While typically delta S is usually joules, so those are typically the units associated with it. Now, one of the things that we can use entropy to help us decide is whether or not a reaction is going to be spontaneous. And to use entropy to do that, we do have to calculate, as we talked about at the end, I think last time, the delta S of the universe. And basically, the universe is made up of two things, kind of your system and your surroundings. And that would be the delta S of the system, which again, in most cases, is the reaction that you're looking at plus the delta S of the surroundings. And if you add those together, and you end up with a positive value for delta S of the universe, the reaction will be spontaneous. And obviously vice versa there, if you end up with a negative value, we're going to be looking at a non-spontaneous process when we calculate the delta S of the universe. We're going to talk about how to calculate each of those things, the system and the surroundings, in just a second. But once again here, it will be spontaneous if it's positive, non-spontaneous if it's negative. And if it equals zero, we will be at equilibrium at that point. So as we talked about with that, the idea behind that is, as we know, when we reach equilibrium, the rate of the forward direction equals the rate of the reverse direction. So net, what happens is everybody pretty much just gets locked into place in terms of their concentrations. So overall, in terms of the craziness and disorder, you're not really displacing anybody, because even though there's a lot happening, everybody's still maintaining pretty much where they're at. So there is no overall kind of more craziness happen on the right or the left, because it's at equilibrium in that situation. Any questions on that stuff? All right, then let's get into the two parts to the delta S of the universe and how we calculate it. The first one is the entropy change of the system. And as I mentioned before, it typically is the reaction that you're looking at. And basically, you would go to a delta S table, which I think we might have saw last time, and you will look up these values. And much like we do with, thank you, much like we do with delta H, we take our delta S, and it is the delta S of the products minus the delta S of the reactants for our system or our reaction. And a lot of the idea here is entropy, enthalpy, Gibbs free energy. These are all state functions. And once again, state functions really are only sort of worried about sort of where you begin and where you end. The sort of journey to get there is not all that important. Your initial condition and your final conditions is really what is of importance. Because in a chemical reaction, again, as we might have touched upon last time, you have your reactants that go to your products. So really, in a chemical reaction, when you look at that situation, this is your initial conditions, this is your final conditions. And that's why for things like delta H, delta S, and these things, we always tend to take products minus the reactants to figure out where we ended up versus where we started in these sort of situations. And like I said before, delta S is a little bit different than delta H. You will actually find values for things like O2, H2, things in their standard state. Remember, from delta H values that you would look up in a table, if you had anything in a standard state that's uncombined, and just kind of naturally how it comes, they have a value of zero, but you will actually find values for delta S. The other thing that's kind of different for delta S values that you find in the table is they typically are all positive values. So they're all typically positive values. And like I said before, they're typically in joules as well. So if we wanted to calculate this, these are some of the values there. And I'm missing one there. We'll just borrow the table. It should be around there somewhere and find that one. I think there it is. I think it's on this table. I can steal it. Looks like 213.8. We'll go with. There it is. Let's see here. So these are some delta S values you can get from the table. Try to remember, I just said they're 213.8, I think. That sounds pretty good. All right, so that's the delta S from the table for CO2. All right, so why don't you calculate this particular one here and see what you come up with? The delta S for this reaction, our system. Okay, so let's take a look. So once again, very commonly you will have to go to the table and sort of look up these values. They usually just don't give it to you in the problems. So as I mentioned before, in your book, towards the back, there should be usually a thermodynamic table that has S values, G values, and H values in them. Here we are going to do basically our products minus reactants. And again, that's basically how we're going to calculate this. Just like we do with delta H as well, you do have to take the coefficients into account and multiply them by the values that you find in the table. So in this case, our delta S of our system here will equal on our product side. We got two CO2s, so we'll take 2 times the value of CO2 from the table, again, multiplying by the coefficient. And that's going to pretty much take care of our product side. We will then subtract it, and now we'll do our reactant side. We got 2 COs, so we're going to take 2 times the value of CO, which is 197.9. And then we're going to add it to our other reactant, which is O2, which you will actually find a value for in the table, and that is 205. And once again, we'd be basically multiplying by 1 in that case. And that is going to yield us here maybe a negative 173.2 joules in this particular case. Questions on that calculation? Now, yeah, I'm sorry. Yeah. Well, technically speaking, it would be joules per Kelvin in this case. The moles actually cancel out when you're doing the two, because that's basically 2 moles. So that's kind of where the moles go away at this point by multiplying by that coefficient. So I'm good if you just want to leave it with joules, but technically the Kelvin is kind of still there at this point. Yeah. Other questions? So when we do look at the entropy of this system, is the disorder increasing or decreasing? The disorder is decreasing, the amount of order is increasing, right? Things are getting more ordered. That is what the negative means here. Again, we cannot use the delta S of the system or the reaction to tell if this reaction is spontaneous or not. But what it's going to tell us is in this particular reaction, are we increasing the order, decreasing the order, increasing the disorder, whichever one you want to look at, order or disorder. And in this particular case, with a negative delta S, we are definitely decreasing the disorder in this situation. By the way, this is something that you could actually just predict the sign of the value that you get by looking at the equation. And what I mean by that is if we look at this particular equation here and this particular reaction, what we see when we look at the reactant side is I got 2 gas molecules and 1 more makes a grand total of 3 gas molecules on the reactant side. When I get to the product side, I have only 2 gas molecules flying around. So if you think about 3 things flying around your face versus 2, right? It gets a lot less crazy as 3 things flying around in your face. So we decrease the amount of gas molecules in this case, which is actually going to increase the order of everything, that we don't have so much stuff flying around. And we could make a prediction like that. So if you look at an equation and you see that you actually produce less gas molecules than you started with, you should expect when you calculate the delta S of your system for the answer to be negative. Is a good way to check yourself, make sure you didn't make a calculation error. And vice versa, if you actually have a situation where you actually create more gas molecules than you started with, then that's obviously going to create a lot more disorder, right? Because there's going to be a lot more stuff flying around. And you would expect a delta S for the system to be positive in that situation because you're definitely going to be decreasing the disorder. And a lot of times in this chapter, there are a lot of questions that you're sometimes asked like that. They don't necessarily give you numbers or something like that, but they go, hey, under these conditions, what do you kind of expect to happen and stuff like that? Any questions on there? And that's what we just talked about. So again, you could kind of look at the gas molecules and make a prediction of the sign of the delta S of the system. If you actually end up with the same number of gas molecules, then it's kind of a toss-up. You could have a positive or a negative sort of value. It most likely would be a relatively small value for entropy. Because again, in that situation, if you really kind of ended up with the same amount of gas molecules, you didn't really increase or decrease the disorder in that situation because you got still the same amount of things flying around when you started with and when you ended with. So in this particular reaction on the bottom, if we did something like that without obviously doing any type of calculation, just based on the equation, would we expect when we calculate the delta S of the system for it to be a positive or a negative number in this case? Yeah, so if we take a look here on the left-hand side, we actually only have 1 gas molecule. Remember, that's a solid. And on the right-hand side, that's actually no gas molecules. That's also a solid, right? So we went from a situation where we have something flying around to like nothing flying around. So we increase the order in that situation. And with entropy, what that means is obviously we would expect it to be a negative value here in this case because of that. Questions? Now that we talked about how you calculate the delta S of the system, let's talk about the other half of the delta S of the universe, which is the surroundings. And when we talk about the surroundings, there's a couple of things that we have to kind of think about. And one of those things is what type of sort of reaction are we looking at, for example, in the system? Now, we could have obviously a exothermic reaction where energy is going to be released, and that is what we see over here. We have an exothermic reaction where this system is releasing that energy to the surroundings. In that particular case, we would expect actually the surroundings to get a little bit more crazier because they have now just taken in a lot of energy, right? So they're going to have a lot more energy than they had previously. They're going to start moving around a lot faster. And again, just thinking about things flying around, that's going to cause a lot more craziness and disorder to happen. And for the delta S of the surroundings in this case, we would actually expect it to end up being a positive value because it is picking up the energy from the system and causing, again, everybody in the surroundings to go a little crazier, if you will. Now, opposite of that is if you have a system that is endothermic, is going to absorb all that energy and it's going to basically absorb the energy from the surroundings. So in this case, the surroundings is sort of dumping this energy into the system. Now, in the case of the surroundings in this situation, because they're releasing their energy, they're essentially going to kind of slow down, right? They're not going to have as much energy, so they're not going to be flying around as fast. They're going to be a little bit more calmer, if you will. And that is going to create, right, a lot more order in that situation. And for the surroundings in that situation, because it's endothermic, we would expect that the surroundings would be a negative value as we're decreasing the disorder and increasing the order in that situation. So the delta S of the surroundings is proportional to negative delta H of the reaction. That's the proportional symbol there. And what that basically means, if we just kind of think about it, if we have our delta H value and we have our delta S of the surroundings, and this is of the reaction. And obviously, if our reaction is exothermic, we will end up with a negative value for delta H. And this relationship says that the delta S of the surrounding is negative of our delta H. That means that we would have a negative and a negative, which turns into a positive value here when we look at the surroundings. Opposite again is true, as I mentioned, if we had an endothermic, our delta H would be positive. And when we go negative of our delta H, a positive and a negative number will give you that negative number overall for your delta S of your surroundings in this particular case. Any questions on that there? Now, does the temperature of the surroundings play a role in whether or not you'll actually see perhaps a big change or not? And the answer would be yes, it does, right? So, if I lit a match just right here, I could put my hand near the match and not touch the fire, but I could feel the heat coming off, I would imagine, right? Now, if you took that same match and you lit it and you put it into an oven that's really, really hot, right? Um, don't do any of this at home, obviously. Uh, Safety warnings for everybody listening. But if you did that, the surrounding temperature of that oven, if you cranked it up to 550, right, is pretty warm. And the heat coming off of that match is not going to be all that much more energy than was in the oven to begin with, right? So the oven at 550 is probably pretty crazy to begin with. And the little bit of energy coming in, it's not going to make it any more crazier. Maybe just a bit, but not a lot more. So the surrounding temperature does play a role in terms of, whether or not you'll kind of see that. So under normal conditions, kind of regular conditions, an exothermic reaction will have a greater effect on the surrounding entropy than if obviously at a much higher temperature where everything's crazy to begin with, it may not have as big of an effect on it. And vice versa, obviously, if you had a much cooler temperature, a really low temperature, and you had some type of exothermic, it would have obviously a pretty good effect as well. Any questions on that? All right, so now that we understand sort of what's happening with our surroundings, and there is an equation for our surroundings, which is definitely all jumbled up there. So let me just rewrite it over here. The delta S of the surroundings is equal to minus delta H of your system or your reaction, whichever one you want to talk about it, divided by our temperature. And this does need to be in Kelvin since all of our thermodynamic values have Kelvin in the units. Your temperature does need to be in Kelvin. So basically, the delta S of the surroundings is equal to minus delta H over T. And our delta S of our system, as we saw earlier, is the delta S of our products minus the delta S of our reactants. So now we understand how to calculate both the delta S of the system and the delta S of the surroundings. Now, a couple of things about this is this equation right here, which is how you calculate the delta S of the surroundings. That's important to remember that there is a negative value in this particular one. And again, is for the reason we just talked about, sort of the opposite relationship. The reason I'm pointing this out is later on in this chapter, we will end up with an equation that looks exactly like that, except there is no negative in it. So if you're calculating the delta S of the surroundings, it should have the negative for that relationship. Later on, we get to an equation that looks very similar to this through a different equation, and that will not have the negative. So it's very common people will kind of throw the negative in always when they get something that looks like that. So if you're not directly sort of calculating delta S of the surroundings, it probably should not end up with negative. You should just rearrange the equation like you normally would, and you'll end up without the negative in that situation. And obviously, the importance of both of these are the two components that you need to calculate the delta S of the universe to help us determine whether or not a reaction will be spontaneous. So individually, these, again, do not tell you individually if the reaction is going to be spontaneous, but when you take kind of the whole picture together, what's happening in the system and what's happening in the surroundings, and put them together and calculate that delta S of the universe, that will allow you to determine whether or not this reaction will be spontaneous or not. Any questions about that? All right, then let's see if this reaction here will be spontaneous. So we want to calculate the delta S of the system and the surroundings and see at 25 degrees Celsius, will this reaction be spontaneous? There's some delta S values on the bottom that you, again, would find in the table, and we have our delta H value given to us as well. So take a few moments there and see what you come up with. Okay, let's take a look and see. So we want the system and the surroundings here. And ultimately, we're going to use that to calculate the delta S there of delta S of the universe. And we need both of those. So we'll just start with the delta S of our system, again, our reaction. Once again, if they're not provided for you, which they probably won't be, you do need to go to the table and look those up. Again, we're going to do basically the delta S of all of our products minus the delta S of all of our reactants. We're also going to remember that we, again, do need to take the coefficients into account when we do that. So starting on our product side there, we got 2 of the NH3s, which looks like 193. And that's going to take care of the products. On the reactant side, we got a nitrogen, which looks like 192. Plus, we do have 3 hydrogens, which looks like a 131 in that situation. And that is going to get us here some type of number with some other numbers, maybe. Let's see. Buck 92 plus 3 times 131.5 hidden equals I don't like that number because I punched it in wrong. Let me try again here. Just didn't feel right. Sometimes, it just doesn't feel right when you look at the number, you know what I'm saying? So 3 times 131. That looks a little better. Not sure where that number came from. All right, negative 199 joules in this case would be our delta S of the system. First off, any questions on that there? This again does not tell us if this reaction is spontaneous or not, but it does tell us what's happening in this reaction, which we again could have predicted the sign of our delta S of our system by looking at our equation. And here we go from 4 gas molecules, right, to 2. That is again going from a situation of more disorder to more order. And we would expect the entropy to decrease and end up with a negative sign, which that's good we did there. Otherwise, that whole conversation would have been for nothing, right? So, um, again, these are things you do want to kind of think about as you're doing these calculations. Do these things sort of make sense based on what you're kind of seeing in the equation? Now, for our delta S of our surroundings, which is sort of the other component that we need, that again, as we just talked about, is negative delta H of the reaction divided by our temperature, which again does need to be in Kelvin. So we need to do a little plus 273, gets us a 298 Kelvin in this case. Here is our delta H that's given to us, so we can just plug that in. And I'm going to go, don't forget, we have a negative in the formula and a negative here in the actual number. And that's going to be 92.6. I'm going to actually multiply it by 1,000. And the reason I'm multiplying it by 1,000 is I'm just thinking down the road. I want my number to be in joules rather than kilojoules because this number is in joules and I got to add them together. If you don't do that and you leave one in kilojoules and one in joules, then you go add them together, you might get an X right on your paper. You don't want that, right? So you want to kind of make sure everybody's in the same units, especially we're going to eventually be adding these guys together. We're going to divide this by 298 in this case, and that's going to get us a 92.6 times 1,000. Double negatives can turn it into a positive. 298 dividing, going to yield us a 311 joules. Obviously, if you left it in kilojoules, you got 0.311 kilojoules at this point. Yeah, which should also be positive. Now we think about this reaction, and we think about this reaction, which is at 25 degrees Celsius, which is like normal temperature. And this reaction is endothermic or exothermic? It is exothermic because it is negative, right? Delta H. And as we just talked about under regular conditions, exothermic reaction should increase, right? The amount of disorder and craziness in the surroundings, which means our surroundings should end up with a positive value for S, which we did as well here, right? So again, all these things should make sense when you sort of think about it. All that's left is to do a little bit of adding, which it's a 50-50 chance today for me. We'll give it a try. So we're going to take our two values, which again, in my case, are both in the same units. If yours are not, you need to make sure you get to the same unit. Once again, it doesn't really matter the unit, but they do have to be in the same unit, either kilojoules or joules. I'm going to go a negative 199 joules plus a 311 joules. And that's going to get me a positive 112 joules in this case, or if you did kilojoules, 0.112. So I finally got to the universe. My universe is positive, which is a good thing, right? You want to have a positive universe. That means this reaction isn't going to be spontaneous under these conditions. The answer is yes, it is going to be spontaneous. We have a positive delta S of the universe. So this is going to be a spontaneous reaction. Once again, this is also a good example of what we were talking about earlier as well, that this is a spontaneous reaction, but if you do this without a catalyst, this might take you a little while to get this reaction to go. So again, remember that when we're talking about spontaneity, we're talking about this reaction should occur if we just leave it alone. And again, it should start to head towards the product side without any, again, outside sort of interference that's happening. Any questions on delta S of the universe? Our Happy letter S. All right, we're doing so great with our new letter. Let's go and talk a little about the third law of thermodynamics. And we kind of touched upon this a little bit, but third law of thermodynamics is the entropy of a perfect crystal substance is zero at absolute zero temperature. If we go back to our Boltzmann equation, clearly if you get a perfect crystal, only one way to be perfect, they say, right? So there's only one microstate, which is obviously going to give us a natural log of 1, which will give us a 0, and that's going to give us an entropy value here of 0. As we can see here, this is kind of like a entropy sort of graph here, and we have our different phase changes that occur. And obviously, we are increasing the entropy as we do that. And that's what you can see here. We're going definitely increasing the entropy as we go from solid to liquid, a much bigger increase in entropy because as you go from solid to liquid, everybody's still near each other, but there's a little bit more room for movement. They have a little bit more energy. That's why liquids are fluid, right? Because they can pass each other. You can pour them out of the beaker. But once you go from liquid to gas, you're completely breaking everybody apart into the gas phase and they're flying around. So there's definitely a lot more increase in the disorder that's going to happen in that transition. This is also related to a couple of enthalpy values that we will see a little bit later on as well. Perhaps you remember that when you do a phase change, as you go from solid to liquid, or liquid back to solid, that does occur at the same temperature, right? It just depends on what you're doing. So, for example, for ice or water, that is 0 degrees Celsius. At exactly 0 degrees Celsius, for example, for water, you have actually both phases in equilibrium with each other. So you have like ice crystals, got a little bit of solid, got a little bit of liquid sort of happening right exactly at 0 degrees Celsius. Not until you get above 0 degrees Celsius that kind of fully transitions to liquid, and not until you go a little bit below 0 degrees that it transitions fully to ice and solid in that case. But it does happen at the normal freezing point or melting point of a substance. And there is an amount of energy required to do nothing more than just change the substance from solid to liquid without changing the temperature. And maybe you remember this guy, that is the delta H of fusion. Yeah. Or the heat of fusion is the energy required to change a substance from solid to liquid or backwards from liquid to solid. For example, for water, which happens at 0 degrees Celsius, and it's about 6.02 kilojoules per mole, are roughly 335, give or take, joules per gram, is the energy required to change ice at 0 degrees to liquid water at 0 degrees, or if you go in the other direction, liquid water at 0 degrees back to ice. And it is sign dependent. So if we're going from solid to liquid, that is an endothermic process, which means it would be like a plus 335 joules per gram going in that direction. And if we go from liquid back to solid, we have to release that energy. Everybody slows down, they lock into the solid phase, and it would be an exothermic process of like negative 335 joules per gram. So it is the same number regardless of which way you're going, but the sign will change whether it's an endothermic process or an exothermic process. Similar thing happens as we go from liquid to gas or gas back to liquid for a substance. This happens at the normal boiling point of a substance. And for example, for water, that's 100 degrees Celsius. And the same idea as you're between liquid and gas at 100 degrees for water, you have both phases in equilibrium with each other. So again, you got a little bit of liquid water, you got some steam happening, not till you get above that temperature that goes one way or the other. And for water, roughly it is like 40.7 kilojoules per mole, which is roughly about 2260 joules per gram, give or take. And that is what is known as the heat of vaporization or the delta H of vaporization in this particular case. We also see something that's similar to what we see here as well. And same idea though with this energy value. It would be an endothermic process heading from liquid to gas and an exothermic process heading from gas back to liquid. It definitely, as you can see, takes a lot more energy to do that transition as you go from liquid to gas as it does to go from solid to liquid. And again, it's just for what we just talked about. When you do that liquid to gas transition, they are kind of fully away from each other, breaking apart from each other. So it takes a lot more energy to do that. By the way, obviously, these numbers here are specific for water. And if you're not dealing with water, it will have a different heat of fusion and a different heat of vaporization and different melting points and boiling points if it's a different substance rather than 0 and 100 degrees Celsius. Any questions on that there? Now, um, when we look at these things, by the way, this happens again at the same temperature. What happens when we actually change the temperature and we keep the substance in the same phase? How do we calculate the heat and energy associated with that? So if I have the same substance in the same phase, but I change the temperature, how do I calculate energy and heat in that situation? Let's do a little throwback from the past, a little specific heat action. Yeah, something like that. So a little Q is equal to ms delta T or mc delta T, whoever you took, or msh delta T, whichever one they like to use. But specific heat and specific heat capacity, the specific heat sort of calculation is typically the calculation we do if we have a substance that's in the same phase, but we change the temperature, like you take liquid water from 0 to 100 degrees or something like that. All right. Now that we talked about S a little bit, let's hit the next letter in the alphabet that we're going to talk about, which is Gibbs Free Energy. And Gibbs Free Energy is kind of what it sounds like. It is energy available to do some type of work. And it is typically delta G is the symbol for Gibbs Free Energy. And delta G, much like delta H, these guys are typically in units of kilojoules. And as we saw there, our delta S is typically in units of joules. So there definitely is going to be a situation where you have these sort of values together in a formula, like a situation right in the middle of the screen. And when you do really want to be careful of these units. Again, you don't want to leave one like in kilojoules and one in joules and try to add them or subtract them together. You definitely going to get the wrong answer because you're going to be off by that factor of 1,000. Now, one of the nice things about delta G rather than delta S of the universe, for example, is you could actually determine whether or not a reaction is spontaneous based on the delta G value. So if you calculate the delta G value and you actually end up with a negative value for it, the reaction is going to be spontaneous in the forward direction. It will head towards the product side. And a negative delta G means that we basically have a spontaneous reaction. If you end up with a positive value for delta G, the opposite is true. The reaction is going to be non-spontaneous the way it's written, but some tricky wordplay here. It will become spontaneous in the reverse direction. And that's because if you take a reaction and you reverse it, your reactants become your products and your products become your reactants. You end up with the same number, except the sign changes. So it will go from a positive sign to a negative sign if you did flip the reaction around. Kind of like when you flip a delta H reaction around, the sign of delta H changes. Same idea in this case. And if delta G is equal to 0, the reaction will be at equilibrium. We will see a number of different delta G sort of formulas and ways to calculate delta G. And the best piece of advice I could give you is pretty much this one, which is I would choose the way to calculate delta G based on the question. So for example, if we take a look at this one, this is delta G is equal to delta H minus T delta S. So that's our Gibbs free energy. That is obviously our enthalpy. That is our temperature in Kelvin. And that is obviously our entropy. So if I was given a problem where they gave me a delta H and they gave me a delta S, I would use this equation because it got those things in it there. And it seems like a very good idea to use these things. Again, unit-wise, we do want to be careful because going to probably be kilojoules for that guy. This guy's going to be joules. those guys will not mix if they are in different units. Yeah, so you will not get the right answer. So you're going to be really careful on that. And again, the temperature does need to be in Kelvin in this case. Now, another way that you could calculate delta G is just like we calculate delta H or delta S. And you can go to a table and use what is sometimes referred to as the standard free energy of the reaction, or you could go to a table and look up what is known as the standard free energy of formation, delta GF. And that's basically table values for delta G. And delta G, very much like delta H, you will find for things like O2, H2, and things in their standard state, they will be zeros, kind of like you see with delta H. When you look up delta H of formation in the table, they will also be zeros. They will also be kilojoules. I think we've talked about this, but just a reminder that when you do go to the table and look things up, you want to make sure that you not only find what you're looking for, but you do find it in the correct state. So, if it's aqueous, if it's gas, if it's solid, you want to make sure you just don't like find the formula and it's maybe in the wrong state. You want to make sure that it is in the correct state that you're looking for. Now, something that people sometimes ask, which is like, what's that little dot that we see on all these things, like delta H and delta S and delta G? And what all these sort of knots, which they're referred to, is it basically means that these things are sort of calculated. You can think of it as under, excuse me, under standard conditions. And when we talk about sort of standard conditions, really the two main things that make something sort of standard conditions is if it has anything to do with concentration, everybody's molarity has to be 1 molar if it's sort of standard conditions. If it has anything to do with pressure, the pressure usually has to be 1 atmosphere, sometimes 1 bar as well, but 1 atmosphere. These are typically when you go like to your book in the back and you look up things in a table, these are typically the conditions that you find like in a table. I would also probably add to that that typically in a table, it's usually done at 25 degrees Celsius is kind of the temperature that's usually the temperature it is associated with. And in most problems, if it's not mentioned for some reason, like the temperature and you need it for something, usually you could kind of assume it's 25 degrees and kind of go to those tables. Technically speaking, 25 degrees is not necessarily standard conditions. These are technically the two things that make something under standard conditions. So that's typically what we see with these sort of little knots, and that's what that little table sort of says down there. Again, atmospheres, 1 atmosphere, 1 molar for concentrations is typically standard conditions. So because Gibbs free energy is a state function, we calculate just like anything else. We could calculate the delta G of a reaction by adding up all the delta G values from the table of our products minus all of those guys for our reactants. Again, doing kind of final state minus initial state, just like we do with H, just like we did with S. You also, again, need to take the coefficient into account and multiply it by the values that you find in the table. So if I was doing a problem and they're like, calculate the delta G, and really the only thing you're given is just the equation, like nothing else, I would go find yourself a table and look up the values and do products minus reactants. Again, if you're given H and S, I would use the equation on the previous slide to calculate delta G. So again, sort of based on the information and the problem or whatever you're working on, will probably dictate sort of, how you'll get to the delta G sort of value. Questions on that there. All right, so why don't we give it a go here? What is the standard free energy change for the reaction? That is a fancy way of saying delta G for this particular one. And is it spontaneous at 25 degrees? On the bottom are some delta G values that you could find in a table, including one that's not there, which is O2, which is 0 kilojoules. We're pretty much just given the equation and we want the delta G, which is basically what all that words means there. So once again, probably not given to you in most problems. You'll need to go look them up. And we're just going to do our products minus reactants here to figure it out. So remember, again, we're going to take our coefficients into account as we do it. So starting on our product side, we got 12 CO2s. Each one is negative 394.4. Going to add that to 6 times our waters, which is negative 237.2. That takes care of everybody on the product side. We're then going to subtract it from our reactant side. That is 2 times our 124.5 plus 15 times 0, basically, I guess. And that's going to get us a negative 6405 kilojoules in this case. Questions on that there? Is this reaction spontaneous? This reaction is spontaneous. Again, negative delta G is going to basically tell us that. So again, here we can use delta G directly to determine whether or not this reaction is going to be spontaneous in this particular case. Any questions on that there? Now, as I mentioned earlier, sometimes in these chapters, especially thermodynamics chapters, a lot of times you're not necessarily given sort of numbers or anything like that. You're just told something like this, like, hey, this is positive, this is negative. Do you think this reaction is going to be spontaneous or not? And you can use this equation here to help you to make some of those decisions or kind of help you decide what you expect. So since we have sort of 4 scenarios here, I'm just going to kind of write it 4 times maybe. We'll take a look at each one visually here. We'll just maybe pop one over here, go down this way. That's G is equal to delta H minus T delta S. All right, so looking at our situation here and remembering that, as we talked about before, our delta H is typically in kilojoules and our S is in joules, that our delta H has got like a 1,000-fold jump kind of on our S in a lot of cases. Now, in the first situation, we have a endothermic reaction, which means in this box here, our delta H will be positive. We have an increase in entropy, which means my delta S will also be positive in this case. So in this particular situation, under kind of low temperatures, the back part here, which is smaller than the front part because one's kilojoules, one's joules, will not be big enough to overtake the first number and make it negative, and you'll end up with a positive value. But at very high temperatures, this temperature here will make the back component bigger than the first number, and you will end up with a negative delta G in that case. So this reaction is typically going to be spontaneous at high temperatures, not so much at low temperatures, because in this case, the enthalpy value will overtake really the back part of it, the entropy part of it. And the process is really going to be spontaneous only at high temperatures. If we take a look at sort of this box here, we have an exothermic delta H. So that's going to give us a negative value for delta H. And we also have a positive value for delta S. And obviously temperature is Kelvin, which is an absolute value, which means you can't have negative, it can only be positive. So in this particular case, because our S is positive and this negative is there, I got myself a negative on both sides, which is good. And that means that this reaction should become spontaneous or be spontaneous at any temperature. So that's a really favorable situation, exothermic, and also an increase in craziness. Yes, and we'll get you a spontaneous reaction basically at any temperature that you put in there. If we come down to our third sort of box over here, this is an endothermic reaction, which again means we're going to end up with a positive value for our delta H. And we will have a decrease in entropy, which means that this delta S is going to be negative. Now, the result of our delta S being negative in this case is a negative and a negative is going to turn this back part into a positive number. And now you have basically 2 positive numbers you're adding together, which means you're going to be stuck with a positive value for our delta G no matter what you do. So this reaction is actually going to be non-spontaneous at any temperature because you're always going to yield a positive value for delta G. So those are kind of the worst situations for a reaction to be spontaneous. You have an endothermic process where you're not really spreading out the energy, and then you have everybody kind of relaxing and becoming a lot more order, sort of happy in that sense. So as you can see for number two, spreading out the energy with an exothermic reaction and having a lot more craziness occur because of that is definitely very favorable for a reaction to be spontaneous. And that's what you sometimes hear in thermodynamics, and this stuff is like the spread of energy and stuff like that out is sort of favorable for a reaction to be spontaneous. That leaves us our last box over here, number four. And in this situation, we have an exothermic, which is negative for our delta H. And our entropy is going to be decreasing, which means it's going to be negative. This again is going to turn this back part into a positive. Now, in this particular case, because delta H is in kilojoules, at low temperatures is very favorable because at low temperatures is going to keep this back part smaller than the front part, and that will yield you a negative value for delta G in that case. Excuse me, at higher temperatures, that's going to cause this back part to become bigger than the front part, and that's not going to be good for a spontaneous reaction to occur. So in this situation, if you have basically the spreading of energy, which is good, and kind of a decrease in craziness, which is maybe not so good, you need a low temperature for this to sort of become or remain spontaneous. And again, if you have a higher temperature, you're going to end up with something that's going to be non-spontaneous. Any questions on any of those different scenarios? Okay. And again, there's sometimes very common questions you'll come across in this chapter. And the question is just that, like, this is positive, this is negative, would you expect to be spontaneous? So let's take a look at a reaction like calcium carbonate that breaks apart into calcium oxide and a little carbon dioxide. The delta H for this reaction is 177.8 kilojoules, and the delta S is 160.5 joules. So what would be the delta G at 25 degrees? And is it, as it says there, is it spontaneous? So take a moment, calculate the delta G and see if it is. All right, so let's take a look. So again, this would be a situation where obviously I'm given a delta H and I'm given a delta S. So obviously should perhaps use the formula that has both of those guys in there. And that is this formula here, the one we were just looking at. Delta H minus T delta S. Popping in our numbers here for 25 degrees, which obviously is 298 Kelvin. We add our 273 to it. Going to give us 177.8. Once again, I'm going to multiply by 1,000 to put it in the same units as my delta S. You could obviously convert your delta S to kilojoules if you like. Minus 298, which is my temperature, and my 160.5 joules in that case. And if I do that there, we're going to end up with looks like about a 129971 joules, or a little rounded there, 130 kilojoules. In this case. First off, any question on the calculation? Is this reaction spontaneous at 25 degrees? This is non-spontaneous at 25, right? And again, we can definitely see that the chart here, 25 is probably way back here, actually. It looks flatline. And this is a chart of pressure versus temperature. And our pressure of CO2 would only happen if this reaction took place. Otherwise, you don't have CO2, then you wouldn't have any pressure, which is clearly what we got going on. Now, can we use this equation to help us figure out maybe when this reaction might become spontaneous if possible. And we know that in order for it to become spontaneous, delta G needs to be negative. That's on the other side of zero, I think. So if I set delta G equal to zero and take the rest of my equation and solve for my temperature, I get something that looks like this. Then a little dividing gives me my temperature is equal to the delta H divided by the delta S. Now, popping my numbers in there, once again, I'm going to take my 177.8 and times it by 1,000 to convert it to joules. I'm going to divide it by my S, which is in joules. And once again, you got to make sure you're in the same units. We're going to go 177.8 times 1,000 divided by 160.5. Going to give us an 1,108 Kelvin in this case, which if I do a little 273 subtraction to get my temperature in Celsius is about 835 degrees Celsius. Is the minimum temperature at which this reaction would become spontaneous. Heck, there is an 835 on the graph, so that's good, I suppose, right? So that is the point right here where this reaction really becomes spontaneous. And we could see that on the graph because at that point, I got some pressure happening. And once again, the only way to get pressure is to make this guy. And the only way to make that guy is for this reaction to actually take place. Now, you may ask, isn't it kind of making a little bit of pressure before we get to that number? And the answer it is yes. But at 835, we are essentially right here at the magic number of 1 atmosphere, which is standard pressure. So at that time, we hit basically standard pressure with that temperature. So this is, again, a useful sort of aspect of this equation. You can kind of rearrange if you have a reaction that is non-spontaneous. In certain cases, you can use this equation to figure out at what temperature it would become spontaneous. Now, what we know about this equation and what we just talked about on the last slide is this was a situation where our delta G is equal to delta H minus T delta S. This was a situation where we had a positive value for H and a positive value for S. And as we talked about in the last slide, because this guy is larger, we would need our temperature to be very high in order for our negative part here to overtake our positive part. So we need a really high temperature for the entropy part of this reaction to be more important than the enthalpy part in this case. And I would say 835 degrees Celsius qualifies as a very high temperature that will accomplish that. And by doing so, creates a lot more disorder. And now entropy in this situation is actually more important than the enthalpy of the reaction. Any questions on that there? Yeah. All right, try one more here to finish it up on for the following reaction. Delta H is negative 1204 and delta S is negative 216.4. At 25 degrees, are the reactants or products favored? H given to us and an S, so we'll use our equation. And our temperature is going to be 298 as we had 273 to our 25. So popping our numbers in here, negative 1204. And again, like I've done before, I'm going to multiply by 1,000 and convert it to joules, minus 298 Kelvin, and our minus 216.4 joules in this case. That's going to yield us here negative 1204 times 1,000 minus 298 times negative 216.4. It's going to get us negative 216.4. There we go. And negative 1204 times 1,000. Looks like it's going to get us here a 1139512.8, I think. And that is negative, by the way, I think. Unless I got the wrong number there, I think. Maybe I do. 11. Try that again. How about negative 1175512 joules? Negative 1176 kilojoules, I think there. Yeah. So look right. Oh, calculator's failing me. Yes. I did. Let me try one more time here because not a banner day here on my calculator thing. I'll try it one more time. I did round it off a little bit here. So negative 1204, right? Times 1,000 minus 298 times negative 216.4. That's the other number, I think. One of the three. How about this number? One of these numbers is going to be right. I know I'm going to get it at some point here. That look better? See, I had it originally. See, they never change your answer. Remember that for Tuesday. Don't change your answer. All right. So we're going to go backwards. We'll go with a negative 1140 kilojoules. Well, I got 2 out of 3. It was not bad on my calculator. So, all right. This means this reaction is going to be spontaneous, and because of that, we would expect this reaction to head in the forward direction, and our products would be favored in this particular case. This again is a situation that we talked about. We had a negative delta H and a negative delta S, which turns this back part into a positive, and that meant at low temperatures like we have here, we would be necessary for this reaction to be spontaneous because at that low temperature, the delta H or the spreading of the energy is again more important than the craziness. Yes. Any questions on that there?